Hello and welcome. I'm Leo Conoy, currently in my third year of Computer Science Studies at Teesside University. Today, I'm thrilled to guide you through my final year project, AstroBuddy. AstroBuddy is more than just a chatbot. It's an educational companion designed to interact with students in Key Stage 2 of the British education system, catering to the curious minds of 7 to 11-year-olds on the subject of space science and astronomy. Built on a foundation of proven technologies, AstroBuddy harnesses the power of an LSTM Neural Network model through the PyTorch framework, engages in natural language processing via the NLTK toolkit, and presents itself through a user-friendly interface crafted with the PyQt5 framework. In this video, we'll journey through the code that breathes life into AstroBuddy, unveiling the mechanics behind the database setup, the intricacies of the user interface, and the intelligence of the response system. Prepare to discover the heartbeat of AstroBuddy and gain insights into the creation of this innovative educational tool. The AstroBuddy project boasts a meticulously organized structure, segmented into various directories, each fulfilling a specific function to ensure the system's seamless operation. Within the data directory, we house our JSON files, forming the foundational dataset that fuels AstroBuddy's knowledge base. The DB directory is the backbone of our project, containing the SQLite database essential for storing and retrieving dynamic content. For visual elements, the project media directory encompasses all the media files integral to enhancing user experience and engagement. The log data directory archives chat logs, providing valuable insights into user interactions and preferences. Central to the project, the SRC directory contains the core application code. This directory is further divided into subdirectories, each tasked with managing distinct application functionalities, from user interface design to back-end logic. This organized framework not only ensures the project's scalability as it grows, but also enhances its readability, making it easier for developers to navigate and contribute to the project. Through such a structured approach, AstroBuddy stands as a testament to thoughtful and professional software development practices aimed at delivering an engaging and educational tool for students. The initial phase of bringing my project to life involved a meticulous evaluation of the data requirements. The British National Curriculum served as an indispensable resource in this regard, guiding the selection of information necessary to enrich user interactions. By adopting a streamlined JSON file structure, I systematically catalogued essential data points. This approach facilitated a dual-layered interaction model, direct engagement with the subject matter, and dynamic interactions with the chatbot itself. Furthermore, it allowed me to address common questions and misconceptions that students within the target age group might have about astronomy. This thoughtful data structuring was instrumental in creating an educational chatbot that is both informative and responsive to the unique needs of Key Stage 2 students. At the initial stage of the project, it was clear that utilizing external JSON files as a data source was a practical approach for setting up our dataset. These JSON files, while not hard-coded in the strictest sense, served as a static and somewhat inflexible foundation for the dataset. However, as the project evolved, the limitations of relying solely on these JSON files for data management became increasingly evident. The need for frequent updates, revisions, or comprehensive modifications to the dataset underscored the necessity for a more dynamic and adaptable data management system. To address these challenges, I decided to capitalize on my SQL expertise by integrating an SQLite database as the primary repository for the data initially outlined in the JSON files. This transition was driven by several compelling advantages that an SQLite database offers over static JSON files. 1. Scalability. The SQLite database supports more complex data structures and a larger volume of data, making it an ideal choice for a project with anticipated growth. This scalability ensures that the project can easily accommodate an expanding dataset without compromising performance. 2. Flexibility. The database structure allows for more straightforward modifications, additions, and deletions of data. This level of flexibility streamlines the development and maintenance process, enabling a more dynamic and responsive data management approach. And 3. Efficiency. Managing and updating the SQLite database is considerably less time-consuming compared to manually adjusting JSON files. This efficiency not only speeds up the development cycle, but also allows for a more agile adaptation to new requirements or insights. In light of these advantages, the project's data management strategy was redefined to incorporate the SQLite database, laying a robust and flexible foundation for ongoing innovation and development. This strategic shift not only demonstrates a commitment to professional and methodical software development practices, but also significantly enhances the project's ability to provide a dynamic and evolving educational experience for users. To facilitate this transition, I developed a script to efficiently migrate the data from the JSON files into the SQLite database. This script ensured that all existing data was preserved and seamlessly integrated into the new database structure, ready for use in training the AI model. By adopting this approach, the project now benefits from a more robust, scalable, and flexible data management system, better suited to meet the demands of an interactive and educational chatbot like AstroBuddy. In my initial foray into model creation, I started with a simple neural network using PyTorch, a widely trusted framework for deep learning. This neural network processed pre-processed input data through multiple layers, delivering an output. Notably, the model's flexibility was a highlight, with adjustable hidden layers and units. While initial experiments showed promising results, concerns arose regarding scalability with potentially large datasets. This prompted exploration into alternative models capable of scaling effectively. Enter the long short-term memory, or LSTM network, a specialized form of recurrent neural network adept at handling sequential data such as text or time series. Utilizing embedding layers to convert text into numerical representations, the LSTM network captures sequential dependencies before generating output predictions through fully connected layers. Given LSTM's proficiency in tasks like sentiment analysis and language translation, it became the natural choice for my AI model, now integrated into the latest version of AstroBuddy. With the AI model set up, the training process begins with the train.py file, leveraging the natural language processing utilities provided in nltk-utils.py, powered by the NLTK toolkit. Data is sourced from our SQLite database and undergoes pre-processing prior to training. This includes tokenization and vocabulary creation, along with the preparation of sequences and labels. Subsequently, a custom dataset and data loader are established for training. The LSTM model is then initialized with specific parameters, including vocabulary size, embedding dimension, hidden size, output size, number of layers, and dropout rate. Training commences employing cross-entropy loss in the Adam optimizer within a training model. Upon completion, the model's state, accompanied by essential metadata such as vocabulary, tags, and maximum length, is saved to a file named data.pth. With our model now trained, the chat.py script handles the operations of AstroBuddy. It interacts with our SQLite database to access the plethora of responses associated with various conversation intents. Upon receiving a user message, the chatbot processes it through the LSTM model to determine an appropriate response. The response selection takes into account the model's confidence level and the availability of relevant responses in the database. If the confidence level exceeds a certain threshold, in our case 80% confidence, and suitable responses are found, the chatbot delivers a response along with a corresponding image. Otherwise, it will gracefully indicate a lack of understanding and request further clarification. This robust system enables AstroBuddy to offer meaningful interactions with users, enhancing their experience. Our graphical user interface, or GUI, is crafted using PyQt5, ensuring a seamless and intuitive user experience. To enhance accessibility, we've integrated a font specifically tailored for individuals with dyslexia, optimizing text readability for users affected by this condition. Following the initialization of the application and the establishment of the user interface, including essential widgets for chat display and message entry, The script gracefully initiates AstroBuddy's warm greeting, inviting users to embark on their cosmic journey. Users can effortlessly engage with the application by inputting messages, triggering responses from AstroBuddy. This interaction is facilitated by robust event handling mechanisms, guaranteeing fluid communication between users and the chatbot. Moreover, the script features a media viewer widget, adept at presenting images sourced from the external repositories or local files. Harnessing the capabilities of NASA's Astronomy Picture of the Day API, the media viewer dynamically showcases captivating astronomical imagery within the application. Through a streamlined design and seamless integration of UI components, coupled with sophisticated image display functionalities, the AstroBuddy application delivers a compelling user experience. By seamlessly blending informative conversations with visually stimulating content, the application fosters a deeper engagement with the marvels of space exploration. Our main.py script acts as the pivotal entry point for our application, orchestrating its functionality seamlessly. Whether it's the initial run or a subsequent launch, the script diligently ensures the presence of essential database and model data. In the event of absence, it swiftly initiates the required processes to create the database or train the model, ensuring the application's readiness for operation. Subsequently, the script proceeds to launch the UI application, empowering users to seamlessly interact with the system. This meticulous orchestration guarantees a smooth, uninterrupted user experience, embodying our commitment to delivering a robust and user-friendly application. After reviewing all the underlying code, here we can see a culmination of that work, with the AstroBuddy application at startup. The application handles the user's query, returning an appropriate response if it has been understood, along with a relevant image if appropriate. To pave the way for AstroBuddy's future evolution, we've identified several promising enhancements and avenues for further development. These include enhanced dynamic image search utilizing the NASA API. This feature aims to dynamically retrieve and present a diverse range of astronomical images in response to user queries, enhancing the visual learning experience. Although its development was initiated, completion was hindered by time constraints, leaving a robust foundation for future expansion. This groundwork promises significant opportunities for enriching visual engagement and educational content. API integration for web deployment. Transform the existing framework into a versatile API, enabling integration into web platforms beyond a standalone graphical user interface. This expansion facilitates broader accessibility and incorporation into diverse educational websites and resources. Dataset expansion and refinement. Commit to continuous improvement of the dataset through further training and development. This includes enriching the existing dataset with new information and refining response accuracy to enhance the chatbot's knowledge base and user interaction quality. Adaptive learning from user interactions. Deploy chat log data from user interactions as a valuable resource for ongoing training and refinement of the model. This adaptive learning approach ensures the chatbot evolves in response to user engagement, improving its conversational abilities and relevance. Automatic model retraining upon database updates. Implementation of an automated system for triggering model retraining in response to updates in the database. This ensures that the chatbot remains up to date with the latest information and optimizes performance without manual intervention. Targeted user testing. Conducting comprehensive user testing with a primary target age group and selected academic professionals. This feedback loop is crucial for assessing the chatbot's effectiveness, usability, and educational value, leading to informed enhancements. Contextual conversation memory. developing capabilities for the chatbot to maintain conversational context, allowing it to recall previous interactions. This feature enables more coherent and relevant responses to follow-up questions, simulating a more natural and engaging conversational flow. Gamification for enhanced engagement, integration of gamification elements such as quizzes, rewards, and progression levels to foster user engagement and learning outcomes. This approach leverages the motivational impact of game mechanics to stimulate curiosity and reinforce knowledge acquisition. Custom AI training module for educators. Create a module enabling educators to input custom data and tailor the chatbot's training on specific topics or curriculums. This customization feature makes AstroBuddy a flexible educational tool, adaptable to varying educational contexts and learning objectives. As we draw this presentation to a close, it's clear that the journey through AstroBuddy's code and design is much more than just an academic exercise. It represents the culmination of years of learning at Teesside University, experimentation, and passion for both technology and astronomy. This project not only demonstrates the application of sophisticated programming concepts and AI technologies, but also reflects a deep commitment to making the wonders of the universe accessible and engaging for learners. While we've explored the potential for future enhancements and expansions, it's important to recognise the solid foundation that has been laid here. AstroBuddy as it stands is a testament to the power of combining educational content with cutting-edge technology to spark curiosity and foster learning. Whether or not this project evolves beyond its current state, it stands as a significant achievement in educational technology and a milestone in my academic journey. I look forward to the feedback from my peers and professors, and I'm excited about the possibility of continuing to develop and refine this project in the future. Thank you for your attention today and for joining me in exploring the stars through AstroBuddy.